This is Laboratory 2 Physics 1. We are going to analyze the motion of a falling object, and we are going to construct two models, one with drag force and another without drag force. We are going to use Newton's second law that states V final equal V initial plus F net divided by mass times delta T. The first step is to multiply mass into both sides of the equation, and then we have the next equation, mvf equals mvi plus fnet times delta t. mv states for the momentum that is represented by a p, and then we can have the momentum principle, that is p final equal p initial plus fnet times delta t, and in algebraic form we can write it as delta p equal p final subtracted by p initial equals fnet times delta t. Well, here I upload my video in Tracker, and I put my coordinate plane and my diameter of the ball. You can see all the transition of time and position I put, and in this little table you can see my time, my position in X, and my position in Y. For this laboratory we're not going to use the position on X, just the position on Y and the time. And here you can see the graph of the video. You can see that it matched perfectly with my video, and because it's going down as in the video is represented. So having the data I took from Tracker, that the first time observation is 0 seconds, the second time observation 0.033 seconds, and my last time observation is of 0.467 seconds, and my first and second position in the negative y-axis, the first one is of negative 0.001 and the second one is of negative 0.021. Then with this information we can take out our average velocity, and we do it by subtracting the position 2 minus the position 1, and the answer we divided by the time 2. So I did this and I got negative 0.61 meters per second. That's my average velocity. So but before we're going to be idle and create our computational model, we have to remember that in our first laboratory net force was 0, but in this laboratory net force is going to change. Net force is going to be the sum of weight plus drag force, and the formulas for both of these are weight equal ball mass times gravity times j hat. J hat states for the unit vector of the y-axis, and drag force equals b times ball velocity. B states for the magnitude of the drag force. You can see that ball mass and B are negative. Why is that? Because the ball is going downward in the negative y-axis. So having all this, now we can go to our viridal model. So this is my model without drag force, the first model without drag force. Here you can see the ball mass, my position vector is in 0 because the ball is dropped from rest, my velocity, delta t, gravity, b, these green words that are going to save me a CSV file for creating spreadsheets on Google, my last observation time. I wrote here the weight, and the net force I just wrote it equal to weight because there's no drag force now. I wrote Newton's second law here and my arrow scale. So we run it and we have this. That here's the computational model without drag force. You can see that my graph matches well with this computational model, and you can see here that the yellow arrow represents the weight, and there's no any other arrow because there's no drag force. Now I will show you a computational model but with drag force. So we change some things here. Let's see. This is important because this will create us the arrows for the representation. And And the thing that is most important here is that we have to change our net force. But here I have to write what means the drag force. So drag force, as we told before, is P times the ball velocity. That we took it, and it was 0.61 meters per second negative. So now we run the model with this model is with drag force. So we run it, and I expect it represents drag force. Oh yeah, look, it represents well drag force. You can see that my graph matches well with the computational model, and here the yellow arrow represents the weight, and the red arrow represents drag force. Well, so it matches everything well till now. But now I will show you my spreadsheet. Here's my spreadsheet. I think you're gonna laugh because this spreadsheet is wrong. I know that it is wrong. I think I have mental problems because I have made this spreadsheet many times and I have never got the results I want, but I don't know how to do it, this spreadsheet. If you know how to do it, please comment the video for you to help me, and the next laboratory I will do it well. Well, having all this, there are two questions we have to answer. The first question is, what does it mean? Examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? Discuss briefly. Well, the one that predicts a terminal velocity is the one I did right now, the one with drag force. I will show you again. Look, this is the one that has a terminal velocity. You may be asking why. That's because it has weight and it has drag force. So we're going to answer the next question, the second one, and it tells, what if, imagine that the object was initially thrown downward, will the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Justify your answer by using your computer models to examine the object's velocity as a function of time, in the case where the object is thrown downward initially instead of dropped from rest. Well, I think, in my opinion, that the velocity will change. Why? Because if it was thrown with a downward and not from rest, then it will have a first initial velocity, and that will cause to change the terminal velocity. So, well, this was my laboratory 2. I expect you like, and thanks. See you later.